Hey, and welcome to this video on bijective functions and set cardinality. In mathematics, we often encounter sets with different sizes or cardinalities. Understanding the relationship between sets of different sizes is an essential tool for solving many problems, particularly in microeconomic theory. In this video, we'll explore the concept of bijective functions and their relationship to set cardinality. We'll learn how to determine if two sets have the same size or cardinality by finding a bijective function between them. But before we get stuck into it, I have a question for you. So I've written this question on the sheet of paper here, and it is simply this: which set has more elements? Option A, the set -1 to 1. So if you have a real number line here, it's all the points in between -1 and 1, excluding the endpoints there. And then option B, the whole real number line, so any real number. And often people, when they have no idea about set cardinality and how complex it can be understanding the set cardinality of infinite sets, they will pick option B because intuitively you can see that every element that is included in set A is also included in set B. Plus you have elements that are outside of set A, like 2 for example, that is in set B, and so therefore the intuition says B has more elements overall. But if you're paying attention, you'll see in the corner here, see, it's a trap, because actually these sets have the exact same cardinality. They have the same number of elements in it. They both have an infinite amount of elements, and that infinity structure is equivalent for both of them. So this is a little hook to get you interested in this, and often people have great difficulty both understanding this and then also proving it. So that's what we're going to look at today in this video. Okay, so before we get into fully understanding that, the idea here is that we can use this important theorem where if a function maps things from x to y and that function is bijective, it proves that the sets x and y have the same cardinality, i.e. the same number of sets, same number of elements in the set. And we use this theorem to therefore prove or identify if two sets do have the same cardinality or not. And to use this theorem, obviously, we need to understand what a bijective function is. So listed here above is a bijective function definition. We just look at a function f that maps things to f of x. Being bijective requires two properties. First, that it is injective, and then second, that it is surjective. These names also have another name, one-to-one and onto. I'll use injective and surjective, but I have seen through a lot of my own maths university classes that people will use either. But these are what those definitions are. So for injective, a function f is injective if f of a equals to f of b implies that a is equal to b. So I'll give you a quick example of a function that's not injective. It's the squared function on the real numbers, because f of 2 is equal to 4, but f of -2 is also equal to 4, because both of those numbers squared is equal to the same thing. And so that would violate this definition, as clearly 2 and -2 is not the same. Okay, surjective. This is slightly different. It says that for all elements in the codomain y, there exists x in the domain such that f of x is equal to y. So to really appreciate this definition, you have to recognize the difference between these two sets. In your domain x, every element in the set gets put into the function, and in your codomain y, the outputs are always existing in this codomain, but not necessarily are all of the elements in this codomain being hit. So often people will send things to the real numbers, but actually only specific real numbers are being hit. And this definition of surjective is saying that actually this codomain y is being hit by something in the domain for all elements that belong to this set y. And our theorem here is that if a function is mapping things from x to y and that function is bijective, then those sets x and y have the same cardinality. Okay, cool. So I think a lot of people benefit from looking at this visually. And I've got just three sets here I've got three functions here that are mapping things to from one set to another set. And understanding injective and surjective in these contexts is quite helpful. So if we look at the first one here, the function is mapping things from the set 1, 2 to the set ABC, and it's sending f of 1 to A and f of 2 to C. We can see that it is injective because everything in the codomain, when it is hit, is only hit by at most one element in the domain. So it's not the case that f of 1 and f of 2 is equal to A, but 1 is not equal to 2. If we know that f of something is equal to A, we know for a fact it must be 1, and same with f of C. And that is what makes it injective or one-to-one. On the flip side, it's not surjective because we have B in this codomain that is not being hit by anything, and so it is not true that every element in this codomain is being hit. Okay, next we have an example of something that is not one-to-one, not injective, but it is surjective. So it's surjective because everything in this set is being hit. A is being hit by 1 and 2, B is being hit by 3, and there's no element that's not being hit by anything. However, it's not injective because f of 1 is A, f of 2 is A, but 1 and 2 is clearly not the same thing. And then lastly, we have this function, which is both one-to-one and onto, both injective and surjective, because every element in the domain is hitting at most one thing, and everything in the codomain is being hit by something. Okay, and that creates our bijective function. So if we can construct a bijective function between two sets, we can use the theorem to then say that the two sets have the same number of elements, because it's impossible to achieve both these properties without having the exact same number of elements in both sets. So practically, we can answer/address our initial question and prove that those sets have the same cardinality by finding a bijective function and then proving that that function is bijective, where the domain and codomain are these two things. And you can generalize this approach to these types of questions where you want to prove two sets have the same cardinality, where step 1, you find a function that is bijective that uses those two sets in its domain and codomain. Keep in mind you can use them in any order, it doesn't matter. And then your next steps, which is 2a and 2b, is to prove that it's injective and surjective. And then the last step, step 3, is to just conclude that because the function is bijective, the domain and codomain have the same cardinality, and therefore, specifically, blah and blah have the same cardinality. Okay, well, let's actually go through and do this. So I've got the proof here, I've done it already, and I will walk us through that proof. So to formally prove it, let's create our function here, f, which maps things from the real numbers 2 minus 1 to 1, using the rule x is being set to x divided by 1 plus the absolute value of x. And that is our f of x function. Any real number can go into this function here, and it will squish the real number into this region, no matter how big that number is. Because if you put in 1,000,000, for example, you have 1,000,000 divided by 1 plus 1,000,000, so that's 1,000,000 divided by 1,000,001, and that's going to be a number that's very close to 1. But we never actually hit 1 because this denominator is always slightly bigger in its size than the numerator. And then we also cover all the numbers between 0 and 1, and then 0 and minus 1, because the numerator has no absolute value, so its sign is determined by the sign of your input. So minus 1,000,000 will get you to the equivalent negative number, as 1,000,000 gets you to the equivalent positive number. And yeah, you can use that to access any number between minus 1 and 1. And what we need to do is prove that this function is injective and surjective. So let's start with our injective proof. For our injective proof, we need to show that if f of x is equal to f of y, x is equal to y. So we can begin our proof by just letting x and y be elements in the domain such that f of x is equal to f of y. And what we want to show is that x is equal to y. Okay, so if we know that f of x is equal to f of y, therefore this equation is equal to this equation. And our goal from here is to simplify it down to just x is equal to y mathematically. So putting the denominator onto the numerator of the other side of the equation gives us this. Expanding it out gives us this. And then simplifying it a step further gives us this. And from here, we want to get rid of those absolute values, but that can be a little bit tricky. So notice that if we could just remove the absolute values here, we'd have y times x minus x times y. That's just going to be 0. And then we have x equal to y. So obviously it's not as straightforward as that, but we're getting close to this mathematical concept where we just have our final step of x equal to y. And to actually remove the absolute values, we need to consider what x and y could be in terms of being positive or negative, and how the absolute values would be impacting it in that context. And we can get rid of those absolute values by actually just taking all possible cases and then applying the consequence of the absolute value in that case and removing it. So there's 4 cases. The first case is that x and y are positive and the absolute values are doing nothing. The second case is that the inputs are negative, and so the absolute values are actually flipping the sign of something like -10, for example, to +10. And then the third case is that 1 is positive and 1 is negative. Oh, sorry, the third and fourth case is that 1 is positive and the other is negative, and then you could have that in 2 ways, x being positive or y being positive. So let's just address those cases. Oh, there's a summary of what I just said. So the first case, if we know that both x and y are positive, then the consequence of the absolute value is nothing. The absolute value of x is x. Absolute value of y is y. And then in this expression, we just get rid of the absolute values from here to here. And that gives you 0, which is the last step of this before getting it to x equal y. Easy. Now, case 2 and 3, this is interesting. If you start off by doing this and do the maths, you actually won't get x equal to y. But the way that we deal with these cases is the fact that if f of x is equal to f of y, it is impossible for this case to exist. So looking back at this expression up here, the denominator is always positive, and the numerator x/y is determining the sign of the whole fraction. And if x is positive and y is negative, then these cannot be equal to each other, which means that it's impossible for f of x to equal f of y and their signs to be different. So those 2 middle cases where you have one positive and one negative x and y value are impossible, and we can disregard those cases. And then lastly, if x and y are both negative, then the absolute value of x is equal to -x. So the absolute value of -2 is equal to -2. And when we plug that into the equation, we get this, which is 0 as well. Easy. So the right-hand side is equal to 0 in every valid case, and so therefore x minus y is equal to 0, and so x is equal to y. That is what makes the function injective, which concludes the injective proof there. Okay, surjective. This one is maybe a little bit trickier to do. So to prove that it's surjective, we have to show that for every element in the codomain, there exists some element in the domain such that f of that element is equal to y. And that is proving that every element in the codomain is being hit by something. So we can do this proof by providing the a that will hit y in the function. Okay, so to do that, we usually find an inverse function and demonstrate that if we put the input into the inverse function, we will hit the y, and then we should verify that that input is a valid input, which is pretty easy for us because it's a real number here. Okay, so first of all, we've got some scratch work. We need to figure out what our inverse function should be. So if we want f of a to hit y, we're trying to find the a to pick that will achieve this. So we can work backwards from this being true to determine what we should set a to be. And if we rearrange this, we end up getting this here. And again, we have absolute values. So absolute values are tricky to work with sometimes, so we need to take cases again. The absolute value of A in this context here is, we basically want to know what A is in terms of being positive or negative so that we can then remove the absolute values appropriately. And if you look back up to this expression here, y is equal to blah, 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 we know the sign of A for this to be true is fully determined by the sign of y. If y is a positive number, then the sign of A must be positive, and if y is a negative number, the sign of A must be negative. And so moving forwards from the step here, we can just set A being equal to a positive number, so the absolute value of A is equal to A, or A is equal to a negative number, so the absolute value of A is equal to negative A, and that's determined based on what your y is. So case 1, if your y is positive and so A is also positive, then we have this expression here, and rearranging that, we get this, A is equal to y minus 1 minus y. So if y was a positive number, so 0.5 for example, we can plug this into our formula. 0.5 divided by 1 minus 0.5 is going to be 0.5 divided by 0.5, which is going to be 1. And so to hit a half, we plug in A is equal to 1 into our function. And we can check that is true. 1/2 is equal to 1 divided by 1 plus 1, which is 1 divided by 2, which is a half. And that is our proof that for this specific value, we have a element in the domain that in the function will hit it. Okay, very similar, which I'll let you read at your own leisure. You can work out what happens when your y is negative, and so you have a slightly different mathematic expression here. Okay, now that we've figured out how we want to achieve our inverse function in our proof, we can formalize this into the proof that y is surjective. At the moment, this isn't actually a proof. This is just figuring out how we achieve the proof. So below is the actual proof. Okay, so to prove that everything in the codomain is being hit, we first let y be something in the codomain. If y is greater or equal to 0, then we choose this. We want to verify that this is valid, so we can verify that this is a real number as y is a real number, and the difference of the division of real numbers is also real. And then also y cannot be 1, so y is a part of this set, so this can never be equal to 1, which means we're not dividing by 0, which means this is very valid. Okay, second, f of a is equal to f of this from our decision, and plugging that in and then rearranging ultimately gives us this. So we've shown that y is being hit, and then we can do the exact same thing for if y is less than or equal to 0, we use this rule, and with the same logic we get down to this. Therefore, we've proven that for every value of y in the codomain, there exists an element of the real numbers where f of a is equal to y. Therefore, f is surjective. Great. And now we prove this injective and surjective, we wrap it up and say this. As f going from the real numbers to the set -1 to 1 is injective and surjective, f is bijective, and thus the codomain and the domain have the same cardinality. And that is actually answering our initial question. I can find it. This. About which set has more elements. It's not B, it's not the real numbers. They have the exact same number of elements. That can be pretty confusing because we can see that the size of the set in terms of distance is longer. It spans on for longer. But when we measure the size of the set in terms of its number of elements, and that size has an infinite amount of elements, it becomes much more complex because this concept of infinity is actually measured and defined through bijections between sets. So if you look at this set of integers, 1, 2, 3, 4, -1, -2, -3, and 0, etc., you can't find a bijection between that set and this set, although the set of integers is also infinite, it spans on forever, but it has a different size, a different level of infinity. So this is introducing you, I guess, conceptually to this idea of infinity being a concept of going on forever, but actually being a size of a number of elements that can go on forever, but vary across different levels of infinity. Okay, so I hope you understood about what a bijective function is, how to prove it, and its relation to set cardinality. Thanks for listening.